Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, it's an honor today to have James Fogarty here from Carnegie Mellon University. James is going to receive his PhD in human computer interaction from the School of Computer Science at Carnegie Mellon this coming spring, where he's been working very closely with Scott Hudson. He's broadly interested in HCI, user interface software and technology, and in how all that's melting into the world in the realm of ubiquitous computing. His interests include human-centered approaches to developing, deploying, and evaluating sensor-based interfaces in everyday life. And you'll be hearing quite a bit about that today in the world of managing and detecting interruptions and interruptibility status of people, as well as some newer work that he's been doing in privacy in ubiquitous computing settings. So, with that, James, take it away.
Thank you, Eric. So as Eric said, this will be constructing and evaluating sensor-based statistical models of human interruptibility. That would be my dissertation title, but near the end of the talk, I'm going to talk more broadly about some of my other interests. And I'm James Fogarty out here from the HCI Institute at Carnegie Mellon. So ubiquitous computing is here. Laptops, PDAs, and mobile phones are a pervasive component of everyday life. They changed how we live, they've changed how we work, and we're more productive because of them. But they still do this. Right? So computers don't have any concept of a presentation. They don't have any concept of a meeting. Current systems generally lack a basic understanding of human social situations and the impact that their actions have on those situations. But compare that to your colleagues. A colleague can typically walk up to an open office door, take a quick glance in, and make a very quick decision about whether or not now is a good time to interrupt. But current systems interrupt or unduly demand attention because they have no way to consider whether now is a good time to interrupt. In an indication that this is a problem, there was a field study done in 2002 by Hudson et al. Showed that managers physically move away from their computer or even away from their office in order to obtain uninterrupted working time. And so these people are getting so many interruptions from instant messaging, email, phone calls, face-to-face meetings, they physically hide in order to be able to have time to get their work done. Another study showed that office workers are interrupted or decide to change tasks approximately once every 3 minutes. And a third study showed a crisis mentality that creates a self-perpetuating cycle of interruptions. And so what this is that I'm up against a deadline. I have a paper deadline or a product deadline. Everybody knows that, so I feel entitled to go ask for help and interrupt somebody. They feel compelled to help me then because they know I'm up against that deadline, but that puts them behind in their own work. So a week later, they're asking somebody else, putting that person behind, and so on. It's this self-perpetuating cycle that's created by interruptions. But you can't just get rid of interruptions. Interruptions are an important part of getting our work done. So a study by Bob Kraut showed that work is accomplished when people are free to communicate with each other. If you remove that communication either by physically separating people or otherwise preventing them from communicating, they're not going to be as productive. The same managers who talked about physically hiding, in that same study they talked about, but you can only do that for a very small part of the day, because being available for interruptions, being available to make decisions is an important part of your work. And if you're not available, you're not doing your job. And finally, a third study showed that 64% of interruptions benefit the interrupted person. So interruptions aren't just about your colleagues leeching off your time and demanding your attention. Interruptions help you get your work done. They bring value to your job. It's an important part of your day-to-day work. So if we had systems that knew whether now is a good time to interrupt, we might be able to do much better than we're doing today. So for example, non-urgent notifications might be delayed until it's appropriate to deliver them. So we wouldn't announce that your battery is fully charged at the beginning of a presentation. And while I faked it here today, pay attention to conferences. It does happen for real. And second, phone systems could inform callers that a callee appears to be busy. The caller could then use their knowledge of their social relationship with the person they're calling, their knowledge of the importance of the call, to decide whether to leave a message or interrupt anyways. And finally, we could have automatic busy flags in instant message clients. So we all know the person who, when they set their flag to busy, we know they're going to be busy for like the next 3 months or so, because nobody ever thinks to unset that flag. But it's very common, so you shouldn't feel bad if that is you who does that. So that wraps up my introduction here today. What I'm going to be going over now are talking about sensor-based statistical models as one approach to this type of a problem. Then I'm going to go over my work, starting with a Wizard of Oz Feasibility Study, then a study of human performance, then a robustness study based on deploying actual implemented sensors, finally a more careful study of task engagement. All of these studies culminate in the development of a tool to support the development of sensor-based statistical models of human situations. I'll then conclude, talk about some future work and some of my other research interests. So going to sensor-based statistical models. Sensor-based statistical models of human interruptibility are one approach to developing systems that can consider whether now is a good time. And the idea here is to collect labels or observations that indicate whether a person was actually interruptible or not at a given point in time, and then learn models by extracting correlations between those labels and the sensed context at the time of the potential interruption. One thing this explicitly is not, this is not the manual configuration of rules that say in this context do this and in that context do that. It's a perfectly interesting and reasonable approach to these types of problems, but it's not the one that I'm going to be talking about today. But the big first question that comes up is say, okay, so we're going to use sensors to model interruptibility. Well, which sensors are we going to use? What are the sensors that we need in order to develop a good model of human interruptibility? And I'm going to take a different approach to that problem. The traditional approach would be a bottom-up one, wherein you develop sensors, deploy them, and then evaluate their effectiveness in modeling human interruptibility. But this approach is prone to failure, and that's because you have no way of knowing beforehand exactly what sensors to build in order to have an effective model of human interruptibility. So you might spend a lot of time and effort building a particular sensor and then find out either that it's just completely useful or that perhaps like a slightly different version of a similar sensor would have been much more useful. So I'm instead going to present a top-down approach. We're going to use HCI techniques to inform the development of a sensor-based statistical model of human interruptibility. And by the end of the talk, I'll show that sensor-based models can identify highly non-interruptible situations significantly better than human observers. So the first study I'll be talking about is this Wizard of Oz study that I did. And the idea here was that, again, we don't know what sensors to build. Right? We have no idea. There's so many different potential sensors to examine. Which ones do we actually spend our time and effort developing? And rather than starting directly from building sensors, we collected audio and video recordings and systematically simulated the presence of a large number of potential sensors. And we're going to then examine the predictiveness of those simulated sensors in order to decide which ones are actually worth the time and effort required to develop them. So I started by collecting a total of 600 hours of audio and video recordings from the normal working environments of 4 senior administrators at Carnegie Mellon University. This was collected for between 3 and 4 weeks for each participant. We go in and we install a computer. It has the recording equipment. I have frames here from 2 of those setups, so you can see the kind of video that we're collecting. Bring the machine in, set it up, and leave. Right? So they're doing their normal work. They're doing it in their normal office. At random intervals, approximately once every 30 minutes or so, we ask them to rate their current interruptibility. This is done with an audio prompt on the machine, and they responded on a 5-point scale. So a 1 would be highly interruptible. I'm just sitting here watching the paint peel off my office walls. And most of these people are in Wien Hall at Carnegie Mellon, which, if you know it, the paint does peel off the walls. And second, the other end of the scale would be 5, highly non-interruptible, so they're extremely busy. I can't believe you had to ask. From these 4 participants, we collected a total of 675 self-reports. This is the distribution here. The thing I want to emphasize is that almost a third of the self-reports indicated that the office workers felt they were highly non-interruptible. So this indicated to us that there are some situations in which office workers clearly considered themselves to not be interruptible. In these other situations, their interruptibility might be more dependent upon the nature of the interruption or who is doing the interruption. But so what we decided to focus on was distinguishing these highly non-interruptible situations, this full third of the data over here, from the other situations. So this is going to be a 2-choice modeling problem where we have to distinguish between these 2 alternatives. The prior probability here is going to be 68%. That's because a naive model would always predict the most common answer, right? And that most common answer in this case would be that the person is not highly non-interruptible. And that would be correct in this case 68% of the time. It's worth pointing out that this characterizes most of our current systems, right? Most of our current systems have no model of interruptibility. They assume that you're always paying attention to them. And for these 4 subjects, this is how often they would have been correct. To develop our simulated sensors, we created custom software and paid employees to watch the recordings and systematically simulate the potential sensors that we were looking at. We looked at all of the different sensors that you might think were related to task engagement or social engagement, and that we could observe in these recordings. So these are things like, where is the person in the office? Are they sitting? Are they standing? Are they at their desk? Are they at a table? what objects are they interacting with, right? So their mouse, their keyboard, are they looking at their monitor? Are they eating? Are they drinking? Are they writing? Are they reading? Are they interacting with a file cabinet? Is their door open? Is their door closed? Lots and lots of different sensors that we could potentially implement. And of course, the presence of guests in the office. How many guests are present? How long have they been there? What are the guests doing? Are the guests sitting? Are the guests standing? Are the guests talking? Lots of different potential activities related to social or task engagement. So we now have this large number of potential features, but you can't just throw all of these into a model because a lot of them won't have anything to do with interruptibility. So we used what's known as a wrapper-based feature selection process. A lot of you may already be familiar with this. I'm going to briefly go over it to help clarify some of the points that I'm going to make later in this talk. But the idea here is that you have this large number of potential features, and you have to decide which ones to include in your model. And the way that we do this is to compute a delta for each potential feature. This is the improvement in the reliability of the model that we would get from adding this particular single feature into the model. Right? So currently our model has nothing in it. So we select the highest delta. What is the single feature that is going to give us the best improvement in our model? And we put that feature in the model, right? So if you're only allowed one feature, if your model can only be based on one particular piece of context, this is the one you want because this is the one that gives you the best reliability for a single sensor. But of course, you're not limited to one piece of context, right? So you compute a new delta for, given that we already have this one feature, what's the next best feature to add? What's the best feature that best complements the one that we already have? And you do that again to get a third feature and so on. You continue until you converge that there's no additional feature to add that gives you a significant improvement in the reliability of your model. And the reason this is important is that throughout this talk today, I'm going to talk about the most predictive feature in a particular model, or the top features that show up in the predictiveness of a model. And what I mean there is that these first features that are selected typically provide most of the predictive power in a particular model. And this is how those features were selected when I talk about those as this goes on. So we use this approach to develop a naive Bayes model of human interruptibility based on our simulated sensors. It identifies highly non-interruptible situations with an accuracy of 79.2%. I'm going to list A primes throughout my talk today. A prime is a statistic that's related to accuracy. People from learning backgrounds will expect to see those today. But I'm really going to focus on talking about accuracy just to keep the talk accessible. But that information will always be there throughout the talk. And surprisingly, the big surprise here was that that first feature selected in this process was a sensor to detect whether or not anybody in the office was talking. We didn't expect this. It's kind of a surprise that a simple sensor that detects whether anybody is talking gives an accuracy of 75.6%. And what this turns out to be is that this is correlated with a lot of other things, right? This is correlated with being in a meeting. This is correlated with having guests in your office. This is correlated with being on the phone. It might be correlated with being particularly frustrated with your computer. So there's a variety of things that correlate here with talking that are all captured by this single simple sensor. Sure?
Is it fair to compare these percentages with the 68% that you get just by always guessing the first category?
Yes, so I'm actually listing probabilities here. So that p less than 0.001 says that this model is significantly more predictive than that 68% accuracy. I didn't say that explicitly. So yes, all these models are significantly better than that 68%. I'm going to be getting you to a much better comparison in the next couple slides here. But the next thing we looked at is, okay, so that particular sensor is relatively easy to build, right? It's a microphone. What else can we get that is fairly easy to build? And so, of course, you can get mouse and keyboard activity, right? That's just software on the desktop. You can get time of day fairly easily. I mean, computers can at least compute that reliably. And you can get an indication of whether or not a person is on a phone. Right? There's lots of different ways we might do that. You might either install software on a mobile phone. You might put a physical switch in between the phone and the wall. Or in some organizations, you could do that using software on the switching device. But regardless, we can build that sensor relatively easily. And it gives us an accuracy of 78.6% using just those features. So the key points coming out of this first study were that practical sensors can support models that identify highly non-interruptible situations. I showed you several models that have an accuracy of approximately 80%. And secondly, if it wasn't for our use of HCI techniques and this top-down Wizard of Oz-based approach, we would have built the wrong sensors. Honestly, coming into this work, we expected that the vision-based sensors that we looked at and simulated were going to be the ones that were going to have the big payoff. We were expecting to have to decide exactly which vision-based systems to go after, but this showed that we didn't have to do that. So the anybody talking sensor is much more predictive than we would have guessed. Sure?
Why do you think vision-based sensors?
Because we expected task engagement to be, so the results that you're seeing here are largely dominated by social interactions, in particular the anybody talking sensor emerging so well. And when you look at the theory, there's more of a balance in those two that we expected, and I'm going to examine that more carefully in one of the later studies. In the sampling mechanism that we use. Okay. Okay, great. But so yeah, the second point is that easy to build set of sensors were as predictive as the full set of simulated sensors that we looked at, many of which would have required advanced vision systems. So we then wanted to do a human performance study. And this is based on the question, well, okay, a model of about an accuracy of about 80%. Is that good? What's the level of reliability we need in these types of models in order to include them in applications? And in particular, we know that people cannot make this assessment perfectly. People do not walk up to a door, make an initial assessment that you're interruptible, and then barge in and demand your attention. Right? If you do that, your colleagues consider you rude, just so you know. Instead, there's this negotiation that happens. Right? You walk in, you glance in the door, you decide a person is interruptible. Right? You then try to either position yourself in the doorway, you might tap on the door, you somehow to try to get an indication from that person that it's okay to proceed with the interruption. If it's not, there's several things they can do. Right? If they refuse to make eye contact with you, you're expected to pick up that it's not okay. They might turn their head so that you can see that they're on the phone. They might continue working on the task that would be interrupted. There's this very subtle negotiation that happens. And what we wanted to examine was the ability of a model to make that initial estimate of whether or not it's okay to attempt to proceed with this negotiation of an interruption. And the way we did that is we brought human observers into the laboratory and we showed them clips of the recordings that we collected from those initial 4 office workers. Right, so we have these continuous audio and video recordings, and at random times in these recordings, the office worker was prompted and they gave us a self-report of their interruptibility. Right, so if you show a human observer the 30 seconds of the recordings from before we have that self-report and have them rate the interruptibility of the office worker, you now have the office worker's self-report and a human observer's estimate at the same point in time, and we can examine the reliability of these human observers estimating interruptibility. We did that using the same 5-point scale, using this custom software to show the videos to the participants. And we found that human observers were able to distinguish highly non-interruptible situations from other situations with an accuracy of 76.9%. And what this says is that both the full simulated set of sensors that I presented in the last section and that easy-to-build set of sensors perform significantly better than these human observers at p's less than 0.001. And interestingly, there was a bias in their estimates. If you expect that their errors were random, half the time they would mistake you for being more interruptible than you said you were, and half the time they would mistake you for being less interruptible than the office workers said they were. But in fact, the bias is entirely one-sided. There's about an 80% likelihood that they were going to mistake you for being more interruptible than the office workers described themselves as being. Sure.
Did the observers know anything about the person they were watching?
No. No. So they all knew they were office workers within Carnegie Mellon. For the sake of the privacy of the office workers, we explicitly ensured that they did not know the office worker. So there's a couple things that are going on here. And for one thing, they were allowed to watch between 15 to 30 seconds of the recordings, which is much longer than you would ever stand in somebody's doorway. And also, we gave half the estimates based on 15 seconds and half based on 30 seconds. There was no difference in their estimates, the reliability of their estimates. So we have a lot of evidence that this was enough time to watch the recordings. The subjects reported being confident in the reliability of their estimates, but they did not personally know the people who were in the recordings. So the key points coming out of this were that our simulated sensors can support models that identify highly non-interruptible situations significantly better than human observers. And second, that the easy-to-build set of simulated sensors does not perform as well as that full set of sensors, but it does still perform significantly better than human observers. Yes?
Did you gather any data as to whether people who are being interrupted had any notion of whether they were highly interruptible for a certain set of people and not for others?
No. So these prompts were, how interruptible are you? And so we focused on distinguishing this 5 versus else. I'm going to be talking about a different measure later in the talk. And if you want to bring up this general question again of interruptible for what, I'd like to keep that for questions at the end of the talk. But it is a very interesting question. But I don't want to spend 10 minutes talking about it now and not finish. But so coming out of this human performance study, the next question that we wanted to look at was, okay, so there's two big ones. Will actual implemented sensors work, right? Because we simulated these sensors by watching recordings, right? Perhaps the person who was watching the recordings used their human brain a little bit too much and simulated something that we couldn't actually implement in a sensor, right? Even though we had specifications of exactly what these sensors could detect, maybe they used their brain a little bit too much. And so we need to account for that. We need to account for the fact that an actual implemented sensor might be noisier than a simulated version. And the second big question was, okay, so these 4 office workers all had fairly similar job responsibilities. They were all like departmental administrators within our university. Do these results transfer to different types of office workers? And so I conducted a robustness study by deploying actual implemented sensors to study a group of office workers with more diverse responsibilities and environments. I studied a total of 10 office workers in the study. This was actually done at IBM Research in Hawthorne. But so the 10 participants were 2 first-line managers. So these are people who we expected to be most like our original 4 participants, right? Their interruptibility is going to be dominated by going to meetings. It's going to be dominated by social engagement. It's going to be dominated by phone conversations. Then we had 5 researchers who program. So this is most of the people in the room today. So this is people who had their PhDs. They do go to meetings. They do read papers. They do write papers. But they also spend a significant amount of their time programming or otherwise focusing on a task. And finally, we studied 3 interns in shared offices. These subjects were interesting because we found this anybody talking sensor was predictive, right? What do you get when you have this environment where there's 2 people sharing an office, where one of them talking may not have anything to do with the interruptibility of the person that you're studying? And so we wanted to examine the impact of that on our models. Based on our Wizard of Oz results and on the literature, we implemented and deployed sensors to detect the audio level in the room. This was done, all of these offices had shelves above the desk. So this was a microphone placed up on that shelf. So it's away from fan noise from the computer. It's away from typing noise and so on. We deployed physical switches to detect whether the phone was off its hook. And 2 motion sensors in each office, one by the door, one by the desk. Software to monitor the level of computer activity on the mouse and the keyboard, and also what the active application and active windows were. And then 2 sensors on each door to detect whether the door was open, closed, or cracked. This hadn't emerged as predictive in our Wizard of Oz study, even though we explicitly considered it. But it's one of these sensors that repeatedly shows up in the literature, and you just expect it to be predictive. I'll tell you again, it's still not predictive, but we deployed these sensors anyways because they're relatively easy to install. We collected this data for between 6 and 10 weeks, prompting approximately once per hour. Collected a total of 1,006 self-reports from these 10 subjects. Again, you see we got basically the same distribution. Fully a third of the data is over here in this highly non-interruptible category. So again, we're going to focus on distinguishing between highly non-interruptible situations and other situations. And the prior probability in this case is 67.9%, approximately the same as it was before. Okay, now if we look first at building a model of just the 2 manager participants, right? These are 2 people who have fairly similar offices, fairly similar responsibilities. Yes?
You've got no variation across 2 populations, but any variation.
Yes, definitely within individuals, they do not all have this same distribution. I'm very interested, as you'll see as this goes on, in modeling. I don't want to have to build personalized models, even though it turns out we do better if we do. So I'm very interested in this, the fact that we can model this across people. But there's obviously a lot of statistical questions to examine if you want to look at individual distributions, normalizing them or whatnot, but I haven't done all of that yet. Okay, so our model of just our 2 managers, if you model just the interruptibility of these 2 people with similar responsibilities, has an accuracy of 92.2%. Again, this is significantly better than the prior for this subset of the data, and it's significantly better than our human observers. And their model is dominated by social engagement. So the most predictive feature in their model is that they're much more interruptible if they've touched their mouse at any point in the past 20 seconds. Right, so it really doesn't matter what they're doing on their computer. If they're using their computer at all, they're more interruptible because they're statistically less likely to be socially engaged. Right? So these people, when they're interacting with the computer, are more interruptible. And as expected, they're much less interruptible if they're on the phone. If you look at a model of the 5 researchers, it has an accuracy of 83.4%. Again, significantly better than the prior for that subset of the data, and significantly better than human observers. But their model's more of a mix of social and task engagement. So they're less interruptible if they're on the phone, or if the microphone has detected that their office was noisy for most of the past 30 seconds. They're also less interruptible if the active window was Microsoft Visual Studio for 2.5 of the past 15 minutes. So if they'd recently been interacting with their development environment, they were less interruptible. So much more of a mix of social and task engagement here. And finally, a model of our 3 student interns has an accuracy of 89.3%. And the noisy environment results in different features being selected here. So whereas the researcher model said that they were less interruptible if the office was noisy in the past 30 seconds, this model selects a feature based on the noise level in the past 5 minutes. So these short bursts of noise were no longer predictive for these interns in this shared office. But you needed an audio feature based on a longer time interval to extract a relationship to their interruptibility. So this said that there are obviously differences in the features selected for these different types of office workers, and that they're obviously interruptible under different types of conditions. But if you ignore those differences, if you lump all 10 office workers together and you model the interruptibility as a group, you still get an accuracy of 78.7%. That's still significantly better than prior, and it's still significantly better than human observers. So this says that individual differences are important. You are going to get better models if you focus on an individual's interruptibility. But there are some features that transfer across a wide variety of office workers, right? These are probably related to social norms that say, it's not polite to come in and start talking in the middle of somebody who's on a phone conversation, right? There are these norms that transfer across a variety of people, and some features that you can capture related to that will give you a significant advantage over the prior probability and even over human observers. Now, the next thing we looked at here was, remember we had this easy-to-build set of sensors from the initial study. And what could possibly be easier to build than just software, right? Let's not install any physical hardware sensors. Let's look at what can you do with just a laptop computer. And as it turns out, most laptop computers have a microphone built into them. In this particular laptop, it's a little hole up here near where the bottom of the screen is. And so on 6 of our participants primarily used a laptop computer. And so for these subjects, we analyzed not only the audio from that built-in microphone that we'd installed up on the shelves above their desk, we also analyzed from the microphone built into the computer. This is a much noisier microphone, right? You can actually hear the person typing on here. You can hear the fan noise kicking in. What's the effect of that going to be on the model? And it turns out that for a model of the 2 managers using only their laptop computer, we still get an accuracy of 88.1%, significantly better than prior, significantly better than human observers, and not significantly different from the model based on the full set of implemented sensors that we deployed here. Model of the 4 researchers has an accuracy of 80.2%. And if you group them all together, you still get an accuracy of 79.3%. So again, significantly better than the human observers, not significantly different from the full set of implemented sensors. To kind of summarize that for you in visual form, since I just threw a bunch of numbers at you, I want to show you here that, again, the blue bars are models based on the full set of sensors that we implemented in this study. The red bars are based on just the laptop. And you can see that all of the models that I've talked about perform significantly better than the human observers, which are this gray line across the middle. And that none of the models based only on a laptop perform significantly worse than the corresponding model based on the full set of implemented sensors. So the key points coming out of that study were that our results are robust with actual implemented sensors across a variety of office workers with diverse responsibilities and environments. Second, that considering individual features did yield better models, but that there are some features that are fairly general and transfer across a variety of office workers. And third, that a typical laptop computer has sufficient sensing to support models that identify highly non-interruptible situations significantly better than human observers. Yes, so that's still from that first study. There's 2 questions that you might be asking that I'll follow up on right away. One is whether it's statistically valid to compare that, and the A prime takes care of that as opposed to accuracy because they do have different underlying priors. The question you might be asking is, well, so these were different types of office workers. And that's something that I can't completely address, in part because we didn't collect audio-video recordings in the second experiment because we weren't allowed to within that environment. So while their interruptibility may be different, I actually believe it would be more difficult to estimate the interruptibility of this larger group of office workers because they do have more task engagement. So they have this interaction with the computer that's very hard to see when you glance in an open office door or when you look at these video recordings. And so I think it would actually have been harder to estimate the interruptibility for a human observer. So I think that difference is actually working against us. So the next thing we did was a study of task engagement. And this is based on the fact that many of the results I've discussed today have been related to a domination of either social engagement, these are the talking sensors and the interactions with other people, or a very high level indication of computer activity, such as what application you're in. And this is very similar to the work that Eric has had and some of his colleagues here, where they've examined such things as electronic calendars, which capture planned social engagement as opposed to actual social engagement. And also he's done some additional audio and video analyses capturing different social situations. But there was this hole in the literature that says, and I would get asked this question, well, what about when I'm programming, right? What does the anybody talking sensor have to do with me when I'm programming? And so the automated recognition of task engagement was an important and under-investigated aspect of models of interruptibility. So I studied this in a laboratory environment. We controlled for social engagement. We did that by bringing programmers into a laboratory. We gave them this realistic programming task. This is the paint task. It's a simple editor where you paint on the task. And there were 5 bugs or feature enhancements associated with this. We said, OK, you have 70 minutes. Here's the list of 5 bugs. Go at it. We'll pay you for each one that you successfully addressed during the time. And they were able to form their own strategies, form their own orders about how they wanted to address the bugs and so on. These were all experienced Java programmers. And while they were working on this task, we delivered randomly timed interruptions, approximately once every 3 minutes. The interruption appeared as you would expect in something like a development environment. It was a blinking notification down in the taskbar. The person could choose when they wanted to attend to it. So in McFarland's terminology, this is a negotiated coordination of interruptions. This isn't something that pops up and makes you deal with it right now. Right? It starts blinking, and you choose when you're ready to attend to it. And then you click on it. When they would do that, they would get a 2-digit mental multiplication task that they had to do. It's been shown to be an effective interruption of cognitively demanding tasks like programming. With computer scientists in the room, when I put this up, I feel compelled to tell you that the answer is 4032, in case you were doing it in your head. Congratulations, or I'm sorry. But so we applied our Wizard of Oz approach using screen capture recordings from 10 initial participants in this study. And one of the things we found there was that the time to respond is a good measure of programmer task engagement. We repeatedly observed that these programmers would finish what they were doing before they would switch over to handling the interruption. Right? So if you're in the middle of an edit, you finish the edit. If you're in the middle of a navigation, you finish the navigation. Then you attend to the interruption that was just delivered. This held... Oh, sure, Ken?
Well, I'm just wondering, what's their incentive to ever attend the interruption at all? Like,
Oh.
You're getting paid for all the bugs. Like, why?
Yes. Okay, so they were told they would be paid $10 for each bug that they corrected. They were told they would lose $2 for each interruption that they either ignored or incorrectly responded to. We didn't enforce that second penalty because it turns out that math is incredibly difficult to do in your head, and we would have done the entire study for free if we actually didn't charge, if we deducted for them doing it incorrectly. And, and also they tended to try to cheat by like embedding calculator down in the corner, and we had to throw out one subject who would embed calc down in the corner. That just kind of provides more evidence that it was actually a hard thing to do in your head. It was an effective interruption. But so we found that they would repeatedly finish what they were doing, then attend to the interruption. And this held even in extreme cases. There were some cases where it took like 90 seconds or 2 minutes before they would attend to this interruption. We thought they had completely ignored it. Turns out they had just copied an entire class, pasted it into a whole new file, and are now going through and changing every little thing that they have to change in this class to make it something different. Right? So this explanation held even in these extreme circumstances. We built models based on observing the recordings, simulating potential activities that we might detect in a programming environment. Only the edit sensor turned out to be predictive here. And so based on that, we developed a low-level event logger and collected data from 20 additional participants while logging the response times to these interruptions. Sure.
Did the multiplication go away after a while?
No, so once you clicked to bring up the multiplication, you were there until you pressed enter on the multiplication dialog. Are you asking, did the notification that it was sitting there pending go away?
Right. Like if I waited too long, it would go away.
No. No, and the longest waits, we didn't have any that were completely ignored. Like I said, when we went and looked at these ones that took 90 seconds or 2 minutes, it was because of this long-term editing immediately after a paste. There was no instance of a completely ignored interruption.
But you would never have
No. They also did not accumulate. Okay?
I guess you have to consider how many were offered, how many
Well,
was that at a custom?
It was relatively constant. They each got about 20 because of the spacing and the time that was allotted for them to complete the task. But so I'm not sure I've completely answered your question there. But none of them were ignored, so it's not like we can examine how many of them did they choose to attend to. Because the penalty was so high for ignoring it. It was a fifth of what they were working on. But so we collected their response times from these additional 20 participants. We applied a clustering algorithm to group their response times and developed 3 clusters. The first, which I'm going to refer to as interruptible, had a mean of 2.28 seconds with an extremely tight standard deviation of less than a second. So this basically corresponded to an immediate switch to attending to the onset of an interruption. There was an engaged cluster that had a mean of about 7 seconds, standard deviation of about 3.5 seconds. We're going to call this engaged. This was a slight delay before attending to an interruption. And then there was a third cluster that was 43 seconds. Right, this is deeply engaged. It took them quite a while to switch over to attending to the interruption. All of these clusters are significantly different from each other. And what I'm going to focus on is distinguishing interruptible situations from these other 2 types of situations. And for this data set, that gives us an underlying prior probability of 58.5%. So I developed a model based on 26 automatically generated features based on the event stream in the state within the development environment. These features were automatically generated using a tool that I'm going to be discussing next. And that model was able to identify interruptible situations with an accuracy of 75.6%. Again, that's significantly better than that underlying prior. The model considers a variety of event-based features. So the recency of editing, as suggested by our Wizard of Oz results within this subtask. Focus switches to or away from Eclipse were predictive. So if you'd recently switched from something like either your running version of the Paint program or perhaps Java Docs open in a web browser, if you'd switched either from or to that between the development environment, that indicated that you were less interruptible. And finally, interaction with the navigation tree control. Right? So there's this tree control on the side of a development environment that lets you move between what file and what method you're looking at. And they were more interruptible if they were interacting with this tree control. And so this shows that automatically generated features can capture some indications of task engagement. And the key points coming out of this were that our top-down Wizard of Oz method, this time we started from screen capture recordings, again pointed us in the right direction to develop these types of models. And second, that some indications of task engagement can be captured by automatically generated features. The opposing point of view would be that you always needed to have manually crafted models of tasks and that you would always follow people through these task models. And this result shows that if you have the labels of interruptibility, you can capture some of these indications of task engagement using automatically generated features.
James, I want to just reflect a little bit about use of the time to respond metric as a measure of cost in that last study versus other notions of cost, like how hard was it to get back on a task. So it might turn out that for reasons we have no idea, exogenous variables, people feel like they're involved in a complex navigation task when they're in their search pane, file manager, file explorer, and therefore they just go over and quickly get the thing out of the way. But it turns out that doing that is really costly in terms of getting back on track to understand what they were doing. We're relying on their own preferences as to when they're stopping versus the actual notion of cognitive dissonance or cost of recovery. Right.
So that in that analysis of the recordings, we did consider several potential measures. We wanted a measure that was actually related to task engagement on the performance of the actual task, and that was one of the ones that we looked at was, okay, so how long did it take them to resume? We ended up settling on the one, we ended up choosing the one related to how long until they switched over to the interruption because that was the one that seemed to be the most consistent in the data. Another one that we did consider was the actual introduction of bugs into the code as a direct result of an interruption. Turned out to almost never happen, in part because it was designed to mirror a good development environment, which didn't just be like, hey, pay attention to me now. It let you choose when to attend to the interruptions. So we looked at a lot of those measures. The one that you bring up is an interesting one, but it didn't appear consistently in our data to the point where we wanted to model it.
In terms of the semantics and the value of using the proxy response time to the alert as interruption ability measure versus something that would actually be more effectively than whether it was consistent or not for your study, the notions of recovery.
Sure. Yeah, I mean, I think it's a perfectly interesting topic to think about different notions of interruptibility in a model. It's the one we picked here. But yeah, there's a lot of information in those recordings. Several papers have been written based on those recordings. So there's a lot of interesting material there. But so these studies led me to develop a toolkit to develop sensor-based statistical models of human situations. And the big question that we're seeking to address there is, well, so how can we take advantage of these results? Right, we've shown these models of human interruptibility. How can application developers take advantage of them? And I developed Subtle. And Subtle is a toolkit that enables the non-expert development of applications based on models like those in my work. The way that Subtle works is you have an application over on the left there, and it pushes labels into Subtle as it collects them. It might be using prompts, like in the studies that I used here. It might be getting its labels in other ways. But these labels come into Subtle. Subtle includes an extensible sensing library. So it's currently focused on a typical laptop computer, as motivated by the results of my work. So it includes analyses of the audio stream from the built-in microphone. It includes analyses of the desktop event stream. We didn't study location in my interruptibility studies, but when you start to focus on a laptop computer, location seems like an obviously important piece of context. So Subtle includes Wi-Fi-based location estimates. Now, of course, you're collecting up all this sensor data in order to build models, so you got to think about end-user privacy. We're never taking the data off the person's machine, but even building up a big log of everything you ever do on your computer, even keeping it on your own computer, it's still a potential privacy risk. So Subtle includes a privacy policy that filters potentially sensitive information before it gets stored as a part of Subtle. And then finally, there's a fully automated model learner. So it runs as a background process on the person's machine. It learns a model based on the labels that the application is providing, and then it provides that sensor-based statistical model back to the application to do with as they want. Now, to talk about toolkits for a second here, and in particular Subtle's design philosophy, toolkits in general can be described in terms of two properties. There's a floor and a ceiling. So a floor is how easy is it to do something simple with a toolkit. So something like HTML is typically perceived as having a relatively low floor, right? It's fairly easy to get started with HTML. You just put a couple tags on, you have a document, it may say hello world, it may say my name is James, but you have a website and it's fairly easy to get started. The ceiling is at what point does it become hard to build something that you want to, given the tool that you've chosen to use, right? So HTML, in turn, has a low ceiling, right? Once you want to start getting away from a static page or something, you really aren't going to be able to do it with just HTML. So the nature of toolkits is such that you typically trade a low floor against a low ceiling, right? If you want to raise your ceiling and allow people to do more with your toolkit, you typically have to raise the floor also, and it becomes harder to get started on using your toolkit. So Subtle's philosophy is based on providing a low floor. The idea here is to enable non-expert development of applications that develop and use sensor-based statistical models. The idea is to get people who aren't experts in machine learning, to get people within the HCI research community developing these types of models and using them in applications and exploring what the interactions are that you build on top of these types of models. And so while I've worked hard to ensure that the ceiling isn't too low, I've made many important aspects of Subtle extensible. Subtle is not a general learning architecture. So if you're coming into it expecting the end-all of machine learning toolkits, that's not what I'm seeking to provide in Subtle. It focuses on this low floor. One of the things that you have to do in order to provide that low floor is provide a fully automated model learner. Right? These people using the toolkit aren't experts in machine learning. They don't know what types of features are effective for different types of classifiers. And so Subtle iteratively applies type-based operators to automatically construct high-level features. And the idea here is that we have a particular sensor, like the list of Wi-Fi access points that are currently detected. So Subtle looks at this and says, okay, this is a list. What do we know how to do with a list? Well, one thing we can do with a list is see if it contains a particular value. Right? And so there's an operator that corresponds to that. There's a list contains operator. So Subtle examines the history of values that have been reported for the Wi-Fi access point sensor, and it identifies a particular value that occurs with a frequency that is potentially interesting. It then generates a new potential feature by adding this operator. So now we have a Boolean feature, right? And well, what are the things that we can do with this feature? Well, let's compute it over the previous 15 minutes. Right? So it decides to apply these operators to generate this new feature that says, has a person been near a particular Wi-Fi access point for how much of the past 15 minutes? So this is now a numeric value, right? And one of the things we know how to do with numeric values is apply thresholds to them. So we can use an optimal MDLP-based discretization technique, compute the optimal threshold, which in this case might be at 10 minutes. So we've automatically, by applying these operators one at a time, we've automatically constructed this feature that says, has a person been near a particular location for 10 of the past 15 minutes? If this Wi-Fi beacon happened to be the one right by my office, this might correspond to have I been in my office for 10 of the past 15 minutes. But the thing to emphasize here is that because these are based on the type, you can change the underlying sensor and it still works. You don't have to specify how these operators should be applied to each potential sensor. Right? So if we change the underlying sensor to be the list of open applications, these same operators can be applied to say, has Windows Media Player been open for 10 of the past 15 minutes? And so in that way, Subtle can allow extensions to both the set of existing sensors, and it can allow extensions to the set of operators, and you can automatically generate potential features to use in a model. And the person who's building the application doesn't have to have knowledge of machine learning techniques. One of the first applications I've built with Subtle, this is Am I Busy Prompter. It's the fairly straightforward extension to running these kinds of studies. The idea here is that it collects self-reports and shares a model of interruptibility with interested applications. It's very similar to the busybody work that Eric and colleagues did several years ago. It puts up prompts at configurable intervals and asks and uses these prompts to build a model of interruptibility. This is really more of just a way to continue running the types of studies that I've run more than it is like a compelling application. But the interesting thing here is that using this, somebody who's not an expert in machine learning, somebody who's really just focused on interactions, can consider an interruptibility estimate in just 6 lines of code. So the 6 lines of code basically correspond to connecting to Subtle, requesting the model from Subtle, evaluating it, and then comparing the result to a threshold. Right? So it becomes that easy for somebody who's not interested in machine learning, who's somebody who's focused on the interaction, to consider an interruptibility estimate in their application. Second application gets more interesting, and what it's doing is called WHISTLE. I've been forgetting to give you my acronyms here, but WHISTLE stands for Watching How You Interact with Sound to Learn About the Environment. I'm quite proud of all my acronyms. Be sure to ask me about them later. But so WHISTLE collects a label each time a laptop's audio is manually muted or unmuted. And it can therefore learn a model of whether or not your laptop should be muted right now. Right? And that's based on such things as your context, what applications you have open, your location, all of these pieces of information that are being collected by Subtle. And it can learn this model in just 16 lines of code. And so all of the work on collecting the labels, storing them within Subtle, having it learn the model, then evaluating the model and deciding whether to mute or unmute your laptop is 16 lines of code. Sure.
How big do these models get, like in terms of database size and how much sensitivity you got?
So it's an interesting question because if you want, it depends on whether or not how much data you choose to keep around. Subtle currently stores the full continuous sensor context. It doesn't really need that because, for example, you only need the sensor context at the time surrounding a label. Right? The rest of it you're not using in the supervised learning context. I'm currently storing all of it. It generates about 3 meg a day of sensor context. So it's reasonable on a 100 megabit network to collect it on a central server, but it gets more interesting if you have people moving off and living on modems. But again, the model is learned on the person's own machine. And so this notion of centrally collecting the data is only relevant in the studies that I run as opposed to building applications for end users. But the thing that really interests me about WHISTLE is I believe this is a first step towards exploring implicit models of human interruptibility. So this notion of like prompting people all the time is kind of paradoxical, and you're not going to be able to deploy applications based on that. But something like WHISTLE, a model of when you mute your laptop probably says something about when are you in a situation in which it's socially inappropriate to make loud noises, right? Because that's why you're muting your laptop, is so that it doesn't do that and doesn't draw that attention to you. And that may say something about your interruptibility. So if we can collect up enough of these types of implicit labels, we may be able to build models of interruptibility without having to explicitly prompt people. And so it's an area of future work that I'm very interested in. And WHISTLE is a first step in that direction. So the key points here were that Subtle enables the non-expert development of applications that create and use sensor-based statistical models of human situations, and that Subtle's philosophy, particularly its focus on typical laptop computer sensing, it has been informed by the studies that I've presented today. So at this point, I'm going to conclude discussing my work on interruptibility, talk about some options for future work, and review some of my other interests. So I've presented a novel top-down approach to developing sensor-based statistical models of human situations. I've shown that a typical laptop computer can support sensor-based statistical models that identify highly non-interruptible situations significantly better than human observers. And I've implemented a tool to enable the non-expert development of sensor-based statistical models of human situations. I'm going to start talking about my future work now, staying with interruptions first, just for continuity. And the one that I just mentioned were these implicit interruptibility labels. And this fact that explicit prompts in order to build a personalized model of interruptibility just isn't a viable approach because these prompts are too disruptive. You're not going to be able to deploy applications based on this approach. But there's a number of natural interactions that I'm interested in using to exploring whether we can use them to build these types of models. Whistle's use of audio was the first example of that. Another example comes from instant messaging and email, where there's this interaction that happens where you get an instant message, there's this little icon blinking down in your system tray. How long does that icon sit there before you click over on it to view your message? Right? This may have something to do with how engaged you were in what you were doing. So I'm interested in examining that. Screensavers are also interesting because there's this interaction that happens where you're not touching your computer, right? Maybe you're giving a presentation, and your screensaver comes on. Now, the first thing you do is immediately hit the mouse because you panic because your screensaver just came on. And that says something about basically you were paying attention to your computer. You were engaged with the computer even though you weren't giving it any input. If you can detect the situations in which that's likely to occur, that may or may not in some way be related to a model of person's interruptibility. And so the thing that I'm really interested in doing is collecting up a large number of these types of different measures and then examining the statistical relationship between these and more explicit indications of a person's interruptibility. So can you build a model that predicts self-reports without ever collecting any self-reports as labels? Can you build it up from just these simple labels, these simple and implicit labels? Another interesting area is the fact that subtle's automatically generated features can sometimes be fairly difficult to interpret. So I'm interested in human interpretable models. If you take a bunch of operators and you chain them together, what you end up with, and when you look at it, it may not be obvious what this means. And so one approach there would be to match patterns in the operator chains to generate natural language descriptions of a feature. But this will only get you so far because, of course, if you take a long and obtuse chain of operators and you automatically generate natural language from it, you're likely to generate a long and obtuse piece of natural language, right? And so I'm very interested in examining feature selection that assigns a complexity score to each operator or each combination of operators, and then selects features that provided a increase in the reliability of the model that's comparable to the addition of the complexity of the model. This is in some way similar to the MDLP work that's widely used in machine learning, but there's a number of important differences there that I'd be happy to talk about with people. And finally, developing hierarchical models based on human interpretable intermediate concepts. So we know in the area of interruptibility that task engagement and social engagement are important. So can we also directly model these intermediate concepts? And can we say, OK, you're not interruptible right now, and it appears to be because you're socially engaged? Can we start to provide these types of explanations of the models to people, both for when they go wrong and for people when people ask why? And lastly, subtle is extensible, and this introduces a problem, which is that I've carefully designed the current set of operators. They use good heuristics, and they search a reasonable size space of potential features. But because it's extensible, a naive user could come along and create an extension that crosses every pair of existing potential features. And they've just shot themselves in the foot because now it's completely computationally intractable to search that feature space. And the ideas here are that, well, we could laugh at them when they do this, or we could actually try to incorporate support into the toolkit to address this. And so I'm very interested in that. The idea is that because subtle can observe this tree structure being generated as it applies operators onto existing features, we can monitor and control the growth of this tree within the toolkit in a general way that is independent of the particular operators that are being used. What I've illustrated here is just removing some features as they're generated before we started examining them. There's a number of different heuristics we could use. In some ways, this is similar to a streaming feature selection problem that's being examined within the machine learning community. And the idea is that you don't know how many features you're going to have, and you have to filter them as you go. One interesting thing that I think is particularly interesting in this problem with subtle is that we're continually learning a personalized model on a person's machine. Right? So we might learn a model from 50 labels, and then a little bit later, we're going to have 55 labels, and we're going to be learning a model again. So we need to take advantage of the knowledge that we had last time we learned this model. And for example, last time through, this particular feature might have been very predictive. And if we filter it the way I've drawn it here, we're not going to be able to generate that feature, and we'll never find it on this search through. And so I believe the toolkit should include the notion that these types of features that have previously been shown to be predictive can be pushed through this preemptive filtering, make sure it's capable of generating that while still maintaining a reasonable size search space.
So throughout all this, you're still using the basic feature selection?
Yeah, so I'm still using information again to do a fast preemptive filter, those types of symmetrical uncertainty things, and then doing a wrapper-based selection.
Some of these properties you're looking for, some of the other
Oh, okay, so you're talking about a different classifier. So I currently learn a classifier that is a decision tree with naïve Bayes models at its leaves. I'm assuming you're talking about ID3, the decision tree, right? Okay. So yes, there's another interesting area of future work which is currently it uses the same type of classifier. And one limitation that comes up there is continuous values, right? You can't predict continuous values. So I'm very interested in different classifiers coming in. But I still think the big issue that's going to come up is you don't have all your features when you start, right? It's this notion of you're trying to filter features as you generate them. If you wait till you go all the way down to your leaves in your generation process, you're already dead because you've already generated far too many features to even compute like the information gain of all of them. Okay, so within the past year or so, I started branching out from interruptions to begin looking at practical sensor-based interfaces as a more general problem. And I want to talk about two pieces of work there. The first is in home activity recognition. Home activity recognition has a variety of potential applications. The one that's particularly motivating my work is elder care applications. So we have a population that's aging. We need to help them stay more independent, live in their own homes longer. But there's this problem, which is that existing approaches are generally either very expensive. You have to go and install sensors throughout the home. This isn't just about the cost of the sensors, right? It's about the cost of physically installing them, taking out the plaster in the wall, ripping up the floorboards to install strain sensors. There's a very real expense here in installing and maintaining the sensors. Either that or it's very intrusive. So you might be asking a person to wear something, or you might be asking to duct tape sensors all around the house. Grandmother's really not going to appreciate it when you duct tape sensors over her painting. And furthermore, elders are likely to reject changes that detract from their home aesthetics, imply a need for assistance, or suggest constant monitoring. Right? There are negative stigmas associated with this that are very real that you have to address if you're going to deploy this type of technology into the home. And the approach that I'm taking is to use the existing infrastructure to reach out into the home. And so in this case, I'm focusing on the water pipes. And so you have all of your water pipes come into your house in your basement, and then they spread out all over the home. And so what we can do is we can put a sensor right here where the cold water comes into the house. Right? We can put another one right here at the hot water heater. And then two more where the water leaves the house, where wastewater leaves the house. So now you've got hot water, cold water, and wastewater. And can you model different activities based on how people use water in relation to these activities? So I explored this in an initial feasibility study by collecting 6 weeks of data in an actual home shared by 2 adults. You can see I taped Berkeley motes directly to the pipe. And there's a microphone pressed right up against the pipe. So it's a very unobtrusive, low-cost sensor, right? It's in the basement. It's taped to a pipe. And I didn't have to cut the pipe in order to install it, right? It's literally a microphone pressed up against the pipe. It's the bandwidth limitations of these sensors mean that you can't continuously record audio and transmit it, so you have to compute features on this sensor. So I computed a couple of audio features and logged them. You can see here a toilet flush as visualized by 2 of these audio features. The bottom shorter peak is the drain that happens when the toilet gets flushed. The longer one is the fill of the tank, right? So you have this short 15-second drain of water, and then you have the longer fill on the cold water. And so we matched activities using rules that looked at these types of patterns in the signals, and I would identify that signal there as a toilet flush. These are relatively simple rules. I think there's a lot of work to do in better recognizers. But even these simple rules basically give you everything but the kitchen sink. And the things that are very mechanical, things like the clothes washer, the dishwasher, the toilet, they have these very fixed durations. They're very trivial to recognize using even these simple rules. The toilet, when we're missing the toilet flush, you can see our recall is down at 87% here. And in this case, it's because it wasn't uncommon for the toilet to be flushed while a person was in the shower. And so the rule matching algorithm that we used couldn't disambiguate the fact that this shower was totally masked by, or that this toilet was totally masked by a person being in the shower. But the information is in the signal, it's just the rules that we used couldn't detect that. So that's one area for future work. What turns out to be hard here is that if somebody uses the bathroom sink or the kitchen sink, and they use it for less than 10 seconds, it's really hard to decide which of the 2 sinks they're using. And that is in part because the sampling rate of our sensors was only once every 2 seconds. So we're getting down fairly close to the sampling rate on the sensors. But it's also because, okay, say somebody uses water for 6 seconds, and they just generate a little bit of cold water usage. How are we supposed to know which sink it is, right? I honestly think the best information it would be to know where in the home they were, right? So if they just flushed the toilet, then it's probably coming from the sink, from the bathroom sink. And potentially time of day also for the kitchen sink, right? Yes, exactly. So there's this type of information. We included a very small amount of that. We did include in these simple rules the notion that a sink activation coming within like a minute of a toilet activation was likely to be the bathroom sink. But there's a lot of room for future work here. Another thing I've been looking at in practical sensor-based interfaces is that the notion of privacy and location-based systems. And in particular, existing approaches to privacy are generally based on the fact that the person is the entity of interest. So this stems from the kinds of applications that people have been trying to build. So if I share my current location with my colleagues, it's inherently not anonymous, right? So all you can control is the fidelity of the location disclosure, right? Do you tell them I'm in Seattle? Do you tell them I'm in Microsoft? Or do you tell them I'm in this particular conference room, right? But there's this new category of applications that are being developed. This is one that was built by ZipDash. The idea here is that it's providing live traffic estimates. The way it's doing it is that you agree with Nextel that this company should have access to your location information. And Nextel is being a good sport about this. They give it to them anonymously, right? And so when they find a lot of people's cell phones are moving very slowly along a particular highway, that implies that that highway is currently congested. But it turns out just not giving them your account number isn't enough to protect your privacy, because they have this continuous stream of GPS information. They can follow you home and look up your address in a database, and now you're no longer anonymous, right? And so the new approach here to privacy is to treat the location as the entity of interest. If you don't care who is providing a piece of information, if you only care about the location that they're describing, it changes the privacy trade-off. So we've developed hitchhiking. Hitchhiking is a software-based approach to location-centric applications. It works on current networks and on current devices. So you can implement applications like traffic flow monitoring, bus location tracking, social hotspot monitoring. So some people like their coffee shops to be full. Some people like them to be empty. You can find out that kind of information based on the devices that are being carried by the people who are currently in those locations. And on a smaller scale, conference room availability, right? So you don't have to walk around to conference rooms to figure out which one is actually empty, even though it's reserved. The person whose laptop is currently in that conference room can share, okay, I'm currently using this conference room. You don't know who I am. You don't know where I am when I'm not in this conference room. But since I'm currently in this conference room, and this conference room is a location of interest, I want you to know that it's currently busy. And so hitchhiking uses the physical constraints of location to ensure that there are no new threats to a person's privacy, even with a malicious application server. So it's easy enough to build these applications if you're just not intentionally revealing a person's location. But we set the higher standard, or a person's identity, I'm sorry. We set the higher standard of assuming a malicious server. And to see how that might work, imagine a conference room application that has knowledge of two conference rooms, A and B, and these are identifiers associated with them. They're probably the indices in a database that this application is using, right? They're just arbitrary identifiers. But the server is going to be malicious and try to track which people use which conference rooms at what times. And so what it does is for each person who asks for the list of conference rooms, it gives them a different identifier, right? And so user 1 gets A1 and B1, user 2 gets A2 and B2, user 3 gets A3 and B3. And now when I'm in a particular conference room and I want to say that, yes, I'm using this, but I don't want to tell you who I am, the only way I have to do that is to give the server the identifier that it gave me. And so now it knows who I am because it gave me a unique identifier when it told me the list of conference rooms. This problem in general is very hard, if not impossible, to address in the general case of purely virtual systems because what makes one random identifier any more valid than another, right, if they're just coming out of a database? But the thing with hitchhiking in our structured privacy analysis is that because we're dealing with location is a physical thing. It physically exists. You can use a sensed physical property to identify the location. And so in the example of this application, our location sensor is probably Wi-Fi, right? And Wi-Fi is based on broadcasting these unique identifiers. They're actually not broadcast. Yes, they are. Sorry. So it's based on these unique identifiers that are broadcast by the Wi-Fi access points, right? And so instead of transmitting that compromised identifier, that A1, our device uses its local algorithm to decide that it's in conference room A. And instead of transmitting A1 to the server, it transmits the same location information that it used to decide that it's in conference room A. The server then has to use that same matching algorithm to infer that, okay, a person is currently using conference room A. But it doesn't have any way of determining that user 1 is in conference room A. And so hitchhiking is based on a structured privacy analysis of these types of attacks on dealing with the information exchange between client devices and servers to enable applications that are focused on locations, collecting information about locations. Finally, last thing I want to talk about is that before I started working on interruptions, I was working on optimization in user interfaces. And this is because numerical optimization allows the system to consider a variety of independent criteria that would be difficult to describe algorithmically. Two of the problems that I looked at here were the generation of aesthetic displays up in the upper right-hand corner here. And the idea here was to define an aesthetic template and do a collage into this. It's defined as a matching problem. And so you solved it using an optimization that would be very difficult to describe how these things are related with an algorithm. I also explored automated dialogue layout using an optimization. But my focus in this work was on creating Gadget. And so Gadget is a toolkit that uses abstractions to make it easier to approach optimization-based generation of interfaces and displays. And so the idea here is that you didn't have to be an expert in an optimization. The toolkit provided a set of abstractions that made this much easier to do. The area that the sort of future work that I'm interested in here is that there's been a lot of work on constraint solvers within the WISC community in particular. And the thing about constraint solvers is you have very efficient solving algorithms, right? It's very quick to solve these constraints. Sometimes it's just like the simplex algorithm. But because you have to describe your problem in this relatively constrained format, you have to use this precise language to describe your problem, it becomes relatively hard to develop these types of applications. At the other end of that spectrum is the Gadget tool that I made. So the abstractions make it easier to develop. But as you start to get into larger applications, it's relatively hard to ensure rapid convergence. And that's because in order to provide these abstractions, we've fallen back on a hill climbing approach. So we can't computationally solve it. We have to do a search through a space. I'm really interested in exploring this intermediate area. What are the abstractions you put on top of constraints that make it easy to develop systems there, but you can still solve them efficiently? And in particular, in this entire area, all of these applications, all of these approaches to applications are currently difficult to comprehend and to debug. So Perl kind of has this reputation of you can only understand it for about 5 minutes after you wrote it. Constraints are worse than Perl in that regard in many ways. It's very hard to comprehend a program that somebody else wrote or even one that you wrote. And so there's a lot of interesting work to do in helping debug these types of applications. So to finish up now, I've kind of broadly summarized my interests. I'm broadly interested in obstacles to the everyday deployment of sensor-based interfaces. Developing reliable models is part of that. I've seen that in my interruptibility work and in the home activity recognition work that I'm getting started on. Practical and appropriate sensing as a part of that. You've seen how my interruptibility work eventually ended up focusing on a typical laptop computer because we got all of the same results without having to use lots and lots of sensors. And you can see that in the home activity recognition too, focusing on these handful of sensors down in the basement instead of lots of expensive sensors throughout the home. I'm focused on privacy and other real-world considerations. You can't really deploy, study, or understand these systems unless you address these real-world things. Privacy is a particularly important one. And while I haven't talked about it so much today, I'm really interested in what are the appropriate interactions. The implicit labels is one example of that. You cannot deploy interruptibility models based on these explicit prompts. So what are the right interactions to build around these things? I think the interactions need to drive the applications, not the models. And so I think there's a lot of work to do in that area. And finally, I believe it's important to develop tools and techniques that enable non-expert development and exploration of advanced user interfaces. That comes through in both my subtle work and in the older Gadget work. So at that point, I'll thank everybody for coming and open up for questions. Thank you.
I wonder if you can talk a little bit about, you promised to talk a little bit about kinds of interruptions.
Right.
And you know, I'm interested in not just the idea of, well, different people are maybe more or less, maybe more or less open to interruptions than different people, but also different kinds of interruptions.
Yeah. So for the tractability of a dissertation, I've really focused on, well, how interruptible are you? And we did describe canonical interruptions to the participants in our studies. And so, for example, the experience sampling studies were based on, okay, so you're receiving an instant message from somebody who works in the same organization, but you don't know this person personally, right? And you don't know what they want, so you don't know how long it's going to take. But there's obviously this interplay, and Eric's looked at this a lot with the decision theory, of how important is the interruption, how interruptible am I, you can balance those against each other. I am somewhat interested, or fairly interested in the fact that you could directly factor those into the model. So right now, the model only considers the context of interruptibility. It would be an interesting area to explore, can we add the characteristics of the interruption in? So now you have features based not only on the context, but also the interruption. And the application that is reporting this label in labels the characteristics of the interruption that it has. So it might know, for example, with instant messaging, it knows who it's coming from. And you can now decide across all of those. The big problem there, the big problem there is the combinatorics, right? Now you've introduced all these additional variables that you have to collect enough data to account for. So there's kind of two approaches, like Eric has done. You have an abstraction, like the value of an interruption, and you have an abstraction of the cost of an interruption. You balance those against each other. Or you can integrate them all into one model. The problem with integrating it all into one model is eventually you have to collect enough labels to be able to reliably solve that problem, which is why, for now, I've been focused on these implicit labels, collecting lots of data, getting that information coming into a tool, and getting that data collected. And then I'd be really interested in using these larger data sets to look at that kind of information. Is that? Okay. Sure.
So you talked a little bit about how your work can help the interrupted sort of manage things like turn off their audio when
Mm-hmm.
What about the interruptor?
Right. So in my motivation, made very clear that interruptions go both ways, right? They're both helpful and caustic sometimes. And part of that is that this mentality of filtering interruptions kind of pervades a lot of this work. But there's also an availability, like sharing an awareness of your interruptions, right? Of your interruptibility. It turns out to be really touchy because there's so many issues that get involved. I didn't talk about it today, but I did develop a context-aware instant messaging system that shared several pieces of your context together with an interruptibility estimate with colleagues. People seem to use that mostly as an indication of whether or not you were present, because that's how they're used to using instant messaging, right? If you're present, then you're available. And so there's a lot of interesting questions there about how you design these applications. Perhaps you muddy the waters between not being present and not being interruptible. Maybe if you're not interruptible, it just shows everybody that you're not there. But that's still not really benefiting the interrupter. Daniel Avrami, who's another student of my advisors, has some work coming out at Kai this year looking at modeling instant messaging availability based on the likelihood that a person will respond to your message, right? And so that's one way to start to look at that problem, is don't treat it as this person wants to be left alone. Treat it as, will this person actually be willing to respond to you now? And I think a lot of the modeling questions are ultimately the same. It's about how you design the interaction around the model. Sure. Okay.
One other thing, I'm wondering if you thought at all about how you evaluate the models. So you have a system, these are for people that are presumably going to have all kinds of their own required desires around what they want to see on the site. So you create a model that create a system that uses some models.
Well, so there's a lot of questions tied up in that. One is, I'll answer part of that. So the evaluation that I want to do in the near term has to do with still believing that interruptibility is a real concept and it's important to model, right? I don't think you went quite that far in questioning the validity of interruptibility, but some of the behavioral people will. And so the way I want to do that is by collecting these implicit labels, modeling them, seeing can these implicit labels predict these explicit prompts. The other question I think you might be asking is, okay, so they make these self-reports. What does that say about what they actually wanted in a given situation? And I think collecting the implicit labels itself starts to address that problem, because you're no longer learning about what a person says they would do with a self-report. You're learning about in what context do they actually mute their laptop? In what context do they actually delay attending to an instant message? And so regardless of what they might say is important, you're starting to develop models based on what they do, which I would argue is the right type of model to be developing in that situation.
And in fact, you might not call it, but really might call it behavior.
Yeah, I mean, there's...
On heads.
Yeah, so there turns out there's this really interesting piece of work that we could do if I want to spend a year of my life watching those old videos, which is that we have these self-reports from these office workers that claim to predict their interruptibility. And the idea is to establish the validity of those self-reports by sitting down with the audio recording, with the audio and video recordings, finding when they were actually interrupted, right? When they got a phone call, when they had somebody come to the door. See if their reactions, as predicted by the context from their self-reports, will predict how they actually responded to naturally occurring interruptions. It's a really interesting notion of predicting validity the other way, right? So I'm planning on using naturally occurring interruptions to predict self-reports. You can try and do it the other way too, which is use self-reports to predict responses to naturally occurring interruptions. It's a really interesting question. It's one that, given all the things that I could have picked to choose to work on a couple years ago, it's not the one I picked, and I'm not sure. Even I'm basically taking that validity for granted as a computer scientist, but for like Bob Kraut being on my committee, it was a very real and interesting question to him. And so I may still end up using that because I do still have those recordings. But I have to find somebody who wants to spend a year of their life watching video.
You Bob Kraut?
What's that? Yeah, maybe Bob will do it. Maybe he'll take a sabbatical to watch my videos.
So, actually, one other question.
Okay.
How do you prevent or cause your tools not to be used in various ways? Like, let's say the CIA really wants me to go to that, they could plant sensors on my sewer pipes, and without
I bet they already can, to be honest. Yeah, it's a great question, and particularly the home activity recognition, which you brought up. There is this notion where installing sensors, and so I give toilet flushes as an example. Some people may consider what time of day they flush their toilet to be a very invasive piece of information. I would argue that putting the sensors in the basement is much less intrusive than putting a camera or a microphone in the bathroom, which is being proposed. I would also argue that my focus, at least, is on these situations where it's giving the person a better quality of life, right? This person is essentially being forced to choose between my child is so concerned about me, I either allow these sensors to be put in, and they are fairly unobtrusive, or there's going to be a much bigger change in my lifestyle. And so there's a very real thing going on there that I think this is a force for good, that particular notion of activity recognition. In general, it's a fair question. What can be done? Right? I am collecting logs, and I do have a privacy policy in place when Subtle collects logs, but there are still ways to abuse that, particularly since it's extensible. What can I do? And it ultimately comes down to, it's not the kinds of questions that I'm addressing as developing a tool. I'm trying to make everything easy, but I mean, it's a place that a developer could make a contribution.
Where can I go to get more information about Subtle?
Subtle's currently a little hard to access. The way to get access is to send me email. That's mainly because I'm in the middle of a job search. I don't have time to support people. I expect to put it online open source probably by the end of the summer. But I'm just trying to limit my cycles on that right now.
I'm also curious, how much, I work on an email box.
Mm-hmm.
I know that we're aware that you like people, there's no frameworks that are already available, like some. How much interest is there in your system with getting stuff like that out there?
It's really hard to gauge because there's a lot of interest within the research community. Every time I mention Subtle in a research audience, I get the, so how can I get access to Subtle question, which is part of why I hesitate on making it available, because they say, we'll just put it open source on the web and people will solve their own problems, but they don't. They send you email. So there's a lot of interest within the research community. It's different interest than I expected, honestly, because I've gotten so interested in the modeling myself. I forget that a lot of people don't really care how the model got built, right? They don't even care exactly what it's modeling. They really just want to say, okay, just give me an estimate of interruptibility, and I'll go from there. And so I'm increasingly thinking it's going to be important to build up a sort of, call it a repository is not quite the right word that I'm looking for, but build up a collection of pre-built models to include with Subtle, and say, here's a model that's based on interruptibility collected from 20 different people. Providing those kinds of additions to just the toolkit functionality are going to be helpful to a lot of people wanting to build stuff with it, I think. And that's the kind of indication that I'm seeing from people who either want just that model. I'm also actually getting people who want just the sensing library because they want to do more traditional context-aware computing, but it's so hard to develop all of these sensors. There's a lot of work going into writing stable code that, it runs in an injected DLL, and if you mess that up, things go badly.
Okay, thanks very much.
Thank you.